Session 15 is exciting. Welcome to Session 15. What I want to do today is I want to pick up and I want to pick up where we left off last class. And if you remember last class, toward the end, I was pretty much at lightning speed trying to cover water reducers. Microphone, oh my goodness. I was so close to not forgetting this all semester long. So rather than go at lightning speed, I decided today I'd use a microphone and try to go at a normal speed. And what we want to do is we want to cover water reducers and air entrainers. And what I did was I went through the water reducer lecture notes and I went through the air entraining admixture lecture notes, and I pruned these out into the notes that you'll see today. So on the website you'll see that there's a modified version of the lecture for water reducers and air entrainer, and that'll be these slides that we're using today. Okay, so I'm going to start off and I'm going to talk about the three main ways that we can use water reducers. We'll talk a little bit about some rheology measurement techniques, and then we'll relate rheology and setting. Then I want to move on into air entrainers. So you'll remember we've got a picture on our right-hand side. The top picture is the system that doesn't contain a water reducer. The bottom picture is the part of the system that does contain the water reducer. And we know that the big difference between these is that the water reducers are acting like a dispersing agent. The water reducer is there to essentially neutralize the charges that are on the cement particles and to disperse the particles from one another. So where we left off, we were talking about three main ways that we could use water reducing admixtures. We also were talking about the fact that water reducing admixtures came in three typical nomenclatures, or three typical levels of performance. We said that there was the conventional water reducers. These were the ones that sort of the ones that first came out. You'll hear these referred to quite a bit. They've got about a 5 to 10% reduction in water. You'll also hear water reducers referred to as plasticizers. So if you see people out and on the field, they're talking about plasticizers. It's the exact same thing as a water reducer. In the mid-'80s, Rocky was king. He was taking on Ivan Drago, and he was breaking him, for those of you who must remember the movie. This is about the same time that the mid-range water reducers started to become popular. The big benefit of the mid-range water reducers, it reduces stickiness, so it had a little bit of preference over the conventional water reducers, especially where flat work was being done, where people were doing a lot of troweling on these mixtures. High-range water reducers then started to emerge onto the scene, and most recently you've been seeing a lot of new types of high-range water reducers. We'll talk about these specifically when we talk about self-consolidating concretes. The main goal here is we're going to reduce quite a bit more water. They're going to act a little bit differently. The way that they coat the surface of the cement particles, they're going to be a little bit different than some of the early materials. We'll talk a little bit about these in more detail. The basic idea here is that we know that the water reducers are going to reduce the water that's inside of the system. Again, civil engineers have become creative in how we name things. So things that reduce water we'll call water reducers. In general, most of the claims that are out there revolve around the fact that performance improves as we reduce water to cement ratio. So you'll see a lot of people claiming other things about the effects of a lot of admixtures, but especially with water reducers, the main claims come from simply the reduction in the water to cement ratio. There may be some other aspects that are sort of secondary effects, but the biggest effect you would get if there was some other way you could reduce the water to cement ratio that wasn't necessarily adding the admixture in. The main effect that we're seeing is the effect of the admixture, the effect of the water reducer itself. Now this began in the 1930s. And the real way it was introduced in the 1930s, they were trying to disperse things like carbon black into concrete to change its color. The main idea is we were constructing at the time quite a few three-lane roads in the U.S. They had one lane going north, one lane going south, and the lane in the middle for anyone who was bold enough to try to get in there and pass. I know I grew up in a region of the world where we had three-lane roads, and it was always very exciting to get out into that middle lane. So in order to try to make roads safer in the 30s and 40s and cut down on some of these accidents, they decided one of the solutions would be to change the color of that middle lane. So they were trying to find ways to disperse coloring agents, and this is one of the ways that water reducers started to come onto the scene. Now the three main effects that we're going to see with a water reducer, we can keep the same slump, and we can reduce the water to cement ratio and thereby increase performance. We can keep the same water to cement ratio and we will get a higher slump, and that'll make things a little bit easier for workability. And then we'll find out that we could also use the same water to cement ratio, reduce both the water and the cement. And when we reduce the amount of cement in the system, we can save some cash. And that's one of the main reasons that you're going to see people that are interested in using water reducers. So the graph that went flying by with a title that made absolutely no sense the last time we met has been revised to a much slower stationary graph now, and a title that I think makes a little bit more sense. On our y-axis we have the flow spread. This is very similar to a slump type number. On our y-axis, this gives us a little bit of a measure of the workability. On our x-axis, we've got something like water content. This is how much water we would have in our particular mixture. And what we'd see is that we would trace out a particular line for each of our mixtures. Here we can see the black line referring to the mixture without superplasticizer, the green line referring to a dosage of superplasticizer that we would add to the system. Now, the first case, we can basically say we want to hold the slump constant. We're going to hold our y value constant. And what we're going to be able to do is we're going to be able to reduce the amount of water that we need in that particular mix. So if we move from the black line over to this green line, you will notice that we've reduced the water from somewhere around 190 kilograms per cubic meter down to somewhere around 140 kilograms per cubic meter. We would end up with a lower water to cement ratio concrete that would give us an overall higher strength. So this is the method that we would use to increase the performance of the mixture. Simply, we're going to maintain the same workability. We're happy with the workability, but what we're going to do is we're going to just simply add the water reducer to drop the water to cement ratio. Less porous system, higher performance. Now, if you were talking to a contractor, they might say, well, I'm not really that excited about making a higher performing concrete. What I'm really excited about is making things a little bit easier on the guys who are placing it out in the field. So here what we want to do is we want to increase the slump, or we want to increase the flow spread, and we could see just a simple way that we're going to increase the slump, increase the workability. We'll keep the water constant, and then we'll move from the line without the superplasticizer straight up until we intersect the line with the plasticizer, and that will tell us that we've kept the exact same water content. But in keeping the same water content, what we've been able to do is we've been able to increase the flow spread from about 375 up to somewhere around 525. So this would be similar to taking something like a 3-inch slump and taking it to a 6 or 7-inch slump concrete. A little bit easier to work with. We haven't lost any performance, but what we have gained is a concrete that's easier to place. Now the next one is a little bit trickier to describe. I want to try to explain this pretty quickly. One of the things that you will notice is our axes have changed a little bit. Our x-axis is water content. Our y-axis is simply the cement content. And I'll sort of take us through this. We could start off with a particular water to cement ratio concrete. Here we've got a 0.45 water to cement ratio concrete. You'll notice that when we plot water versus cement, the water to cement ratio will make a straight line. So the blue line are all water to cement ratios that are 0.45. The red line is all water to cement ratios that are 0.35. If we add a plasticizer, we add a water reducer, we could simply take water out of the system. So we would reduce the amount of water, and we could get over to a point where we've reduced about 40 kilograms per cubic meter of water, and we'd be down to a water to cement ratio of 0.35. Well, if you didn't want to necessarily get a higher strength concrete, what you could also do is, in addition to adding the high range water reducer, what you could actually do now is to reduce the cement and maintain a water to cement ratio of 0.45, but you've done it now with less water and less cement in the overall system. So in doing this, you've taken out about 80 kilograms of cement per cubic meter, and this would result in a substantial savings in the overall process. All right, so those are the three main ways that you could do this. Here is a simple illustration that was taken out of a Concrete International article. Obviously, the one thing I will state here for full disclosure is this is an article written by someone who works in the admixture industry. However, one of the things that the article did quite a nice job of is it said that concrete should go from something that looks like me, a nice fat concrete with lots of cement and water in it, down to something that is more athletic and spry. So what we wanted to try to do is we want to try to reduce the cement reduce the high mortar contents, reduce the paste and sand. So we're going to see we'll go from about 635 pounds of cement per cubic yard down to a concrete that's maybe a little bit more athletic. The way that this can be done is to add the water reducer. It'll reduce the water, it'll reduce the cement, and then we can also get a benefit of the concrete being a little bit easier to place, a little bit easier to use. And in the athletic concrete here, you'll notice that if we didn't add the high range, it would only be 2 inches of slump, but after adding the high range water reducer, it's even a little bit more flowable than what you had in the conventional concrete. So the big benefit here is you'll notice that there was a little bit of an increase in the air entrainer. We'll talk a little bit more about that, but there's a big savings in the cement and really no cost in the water. No huge impact on the slump other than everything was going to get just a little bit better. So the question really is, why wouldn't we want to use more admixtures? And I think this is one of the reasons why you're seeing something like 92% of concrete being made with something other than the big 4 components, something other than water, cement, and rocks. Question?
How much is your high-range water reducer compared to,
Cost-wise?
reducing the amount of cement that you might have in the,
Well, cost-wise, they're going to range in terms of cost. I mean, some of the mid-ranges and the normal, sort of the conventional mixtures are going to be fairly economic. The high ranges can become more pricey because you're getting a huge reduction in the water content.
So, what percentage do you think you could save on per cubic?
We'd have to work out some numbers, but what I could do, rather than just guess at it, what I'll do is I'll work out some numbers and come back and tell you what those numbers are. But I know that they can be more savings than the cement itself costs. So you can actually save money by going in this direction. Okay, but also the other thing that I'm going to point out is a lot of these numbers that we'll talk about they're tricky numbers to get a handle on, because when you buy cement at Menards, it's kind of a fixed number. When you buy cement to do a million cubic yards, you have a negotiation power. And it's kind of the same way with admixture. So if you buy a jug of admixture this afternoon, it may be one price. When you're buying in volume, it's going to be a completely different number. Okay. Is there something I can answer without giving you a specific number?
No, that's fine.
Okay.
I was just making sure that, you were going to save money just in the fact that your high-range water reducer didn't cost as much as just using the extra cement.
My guess is that if they could, they'd charge as much as that you're going to save. But unfortunately, they're not going to get that kind of money back. All right, and I'll get you some actual numbers so that you can get general rough scale of what you could save. All right, for next class. All right, so I'll actually write that down on a list of things. All right. Okay. Other questions?
These superplasticizers do not react with any of these components, right? So how do they exist in the hardened system?
Well, the question has to do with if they react with anything that's in there and how they exist in the system.
In the hardened.
Some of them will be absorbed into the hydrated products. Some of them will stay in the pore solution. Some of them will just stay on the surface of the cement particles. And to say that they don't react the same way water reacts, but you can have an interaction between different things. So one of the things that you will notice is the air entrainer, for example, on this graph. You'll notice that we said that we had to increase the air entrainer a little bit. And sometimes this happens because the water reducer will change the surface tension of the fluid and make it harder to stabilize some of the bubbles. Okay. I'm not sure if that answers the question that you were asking, but okay. So I'm going to just give you this list. You can go through, you can read many of these things yourself. Don't allow it to freeze. Watch out for rusting in the cans, but the rest of it you can read for yourself. Use of rheology measurement tools. Now, we're all somewhat familiar with testing of solids. I think most people that are taking this class probably have a background that's probably more mechanicsy than anything else that we've talked about up to this point. And we're all sort of familiar with the idea that, at least I hope that at this point in our careers, we're familiar with the idea that if we take a material, any material, it will behave a lot like a spring. So if we pull on that material, we will get some sort of a relationship between force and displacement. And the factor that describes this is either going to be the stiffness of the system, or we could get to a point where we could talk about the elastic modulus of the system, and we have a relationship that most of us now take for granted. but when we were sophomores was probably one of the most challenging things that we'd ever experienced in our life. The fact that stress is related to strain through a material constant that we refer to as Young's modulus. Now, at this point in the course, one of the things I'm going to mention, we've got about another 2 or 3 lectures on constituent materials. Then we're going to start to talk about some field operation things, some batching, and then we're going to start to get into mechanics. But before we do this, I wanted to talk a little bit about some of the aspects of the mechanics of the real fresh early age concretes. Here we can see that just like we did with just pulling on a material in tension, we could have also taken a material and we would have sheared that material. And if we sheared that material, we realized that we could relate the shear stress to the shear strain, and we could relate that through a number that we referred to as the shear modulus. So up to this point, everything is elasticity, everything's a solid, everything's linear elastic, and there's not much new that we're seeing. It turns out that in materials that aren't linear elastic solids, we can also get another relationship that relates the shear stress, tau, with the rate at which it's being strained, gamma with a dot. Now the gamma with a dot is simply the strain rate. So here you could think of a plate. The bottom we've got a stationary plate. At the top we've got a plate that's moving, and we could relate the speed at which that plate is moving to the properties of the fluid that's inside of that system. And the properties of the fluid that we're most interested in are the viscosity. And this is basically the property of the material that enables the material to yield consistently or constantly, continually under a constant shear stress. So what we have here is that the shear stress, tau, is related to the velocity or the shear rate, gamma dot, and the way that it's related is our material coefficient, and in this case we're going to call it eta, and this is the viscosity of the material. So if we take a step back, this is very, very similar to what we've seen up to this point. We know that elastic modulus is a material property. We know that shear modulus is a material property. Here we have a material property called the viscosity that simply is related to how things flow. All right? Basically, it's how things flow, how it describes the material flow pattern as a function of time. Now, there are a few ways that we can measure the flow of concrete. We can measure the response of concrete to stress while it's in this Sockwid state. Right? And remember last class that we discovered that Sonic restaurants are the only ones that have something that is somewhere between a fluid and a solid. We also have a material at very early ages that's somewhere between a fluid and a solid. And the only test that we've talked about up to this point that assesses that material that's in a somewhat squishy state is the very famed test called slump. And there must be something that's better than slump. Dumping concrete into a tube, pulling up that tube and letting it sink down over time. There must be something that's a little bit more scientific. And one of the things that people have been doing is they've been looking at using mechanical measures at early age, and this is commonly referred to as rheology. And you'll hear people talk about rheometers. The basic idea is that they will test fresh concretes by applying a stress and essentially measuring how that material moves under a constant strain rate or a varying strain rate. The basic idea here, there are a couple different types of rheometers that are out there. One of them is referred to as a coaxial rheometer. The basic idea here is you would have the cup on the rheometer, which is shown here in red. You'd have the spinning interior portion, which is shown here in green. You would have your sample, which is placed in between these two materials. And I've run out of room to write sample. But basically there's a gap between the inner cylinder and the outer cylinder where you're going to place your material. The outer cylinder usually stays still. The inner cylinder spins. The stress is measured by knowing the torque on the inner cylinder as we rotate it at a constant rate. Now, generally, in order to get good measurements of this, you want to have a ratio between the inner and outer radius of somewhere around 1 is perfect. But obviously that would mean that the material is infinitely small. So usually you're looking at an inner and outer radius of about 1 to 1.1, which means that we need to have a very small wall thickness so that we can do a good calculation of the shear stress. And in order to do this for concretes, we would need something that is huge, something that is very, very large and is somewhat impractical to be taking out and using in the field. So another type of rheometer that people have been looking at is what's referred to as a parallel plate rheometer. Here you've got a stationary plate on the bottom. You've got a spinning plate on the top. The upper plate is going to rotate at a predetermined speed or a predetermined torque. We're going to record. If we run it at a predetermined speed, we're going to simply record the resistance or the torque to that particular speed. Now the big issue here, the benefit is that we can move these plates further and further apart from one another and account for different aggregate sizes. The big downside here is we know that at the center of this, the shear rate is going to be 0. At the outside, we know that the strains are going to be the maximum. So the basic problem here is determining an actual analytical solution is very tricky because we don't have a constant rate. It varies as a function of radius. So the basic idea is we've got one test method that's very clean analytically. We've got another one that's got a whole lot of benefits, and there's a lot of activity going on right now in looking at all of these rheometers. What I wanted to do is I wanted to just sort of relate this back a little bit to some of the things that we're talking about here. Here's a picture of a parallel plate rheometer, typical parallel plate rheometer. This was some work that we had done with Clarissa Ferraris at NIST. So this is the NIST rheometer. Here you can see that it's a parallel plate. Here's the upper plate. Here's the lower plate toward the bottom. And the plate actually has some serrations on it. So it's basically got like a crisscross French fry type cut on the surface, so it can sort of grab onto the cement paste. When everything comes down, it actually is going to live in this little house that helps to supply some moisture, so we're not drying the system out. So this thing will move down toward the sample. We'll squish the sample in between there, and then we'll spin the top plate. If we know the speed that we're spinning it at, we can measure the resistance to that spinning, and we'll have a measure of what's going on. Now this brings us to a couple of the ideas of what it is that we're actually trying to measure. So as I mentioned before, if we have just the sort of the simplest relationship that exists is the Newtonian relationship. So when we talk about the Newtonian relationship, we know that we talk about Newtonian fluids, we're typically talking about something like water. Water is a fantastic Newtonian fluid, and what we would essentially be doing is developing a plot that is the shear stress plotted on the y-axis, the strain rate plotted on the x-axis, and one of the things that we will notice about a Newtonian fluid is that it will always go through a point that's 0, 0. So the basic idea is we end up with a very simple equation. This is what we were talking about up to this point, where the shear stress is related to the strain rate through the material property that we call viscosity. Now it turns out that this is a fantastic equation for materials like water, but unfortunately concrete isn't always like water. Turns out that concrete doesn't necessarily behave like water, and probably the simplest way that we could assume that concrete behaves is something referred to as a Bingham model. And one of the things that we all find out about concrete frequently is that you can't just use one single parameter to describe its behavior. Here we're going to need two parameters. The first parameter is what we will refer to as a yield stress, this tau naught value. So the big difference you'll see between the Bingham model and the Newtonian model is the fact that it doesn't go through the origin, and we have some offset, some yield stress that has to be overcome before the material will start to move. So the equation now is that we've got the yield stress is equal to some value that must be overcome plus the viscosity times the strain rate. So the same type of equation. The only thing is we need to overcome a yield stress. So what is a typical implication of this? Well, we need to do something to get the material moving. It's not just going to flow under its own power. We need to apply some sort of a stress to get that material moving. Once that stress has been exceeded, the material is going to start moving. It's going to move at a constant rate or a constant viscosity. Typical material that you may have run across that exhibits this type of behavior, toothpaste. Right, most of you got up this morning and you weren't clever enough to instantly take the cap off of the toothpaste and have the toothpaste jump out and onto your toothbrush, right, because it wasn't a Newtonian fluid. You took advantage of the fact that it was a Bingham fluid because you took a few seconds and applied a yield stress by squeezing the tube to get the material moving. Same type of thing that we have when it comes to concrete. Now, the one thing that I will mention is the water reducers that we're talking about, what they are typically going to be acting on is this yield stress value. The big goal of a water reducer is really to drive down this yield stress value and make a material try to look more and more like a Newtonian fluid. Now, everything here doesn't load and unload along the same paths. I'm not going to spend a lot of time. You can read the text on your own. Essentially, we would have a material that during loading would follow this red line. On unloading, it would typically go back towards zero. And typically, the area between these two curves is referred to as a hysteresis. This is sometimes caused by hydration or the breaking down of the flocks, especially when we have something like a water reducer inside of the system, where you apply a little bit of material to get the system to break down. Here are some typical values. I'm not going to spend a lot of time on this. Simply just a 0.3 water to cement ratio with different amounts of superplasticizer, 0.42 water to cement ratio, and then we've got something with a little bit of silica fume thrown into the system. You will notice that when we go from the 0.3 down to the 0.3 with more water reducer, we drop off this yield stress value. Higher water to cement ratio, we have a lower yield stress value. Things start to look a little bit more like a Newtonian fluid. A little bit of how this starts to relate to setting, and we will actually spend a little bit more time talking about setting later on in the semester. But relating rheology to setting, I think it's important that we try to do this as we're going through to start to look at how some of these properties are related. Here we can see the temperature rise curve, or the heat curve. Sometimes you'll see this rate of heat evolution, dq dt. And we talked about this earlier on in the semester, where we said that the first period here of this was essentially the wetting of the system. It went into a dormant period. And then I made some statement about we have the end of the second region, the beginning of the third period, the acceleration phase. And at some point during that acceleration phase, we'll start to get setting in the concrete. Some point toward the top, either here, at the top, slightly after, we'll get something that looks a little bit like final set. Well, I want to jump into this a little bit further, because one of the things that we've been doing some work on recently is looking at the rheological measurements at real early ages. And this is a plot, this line that I'm going to trace out right now in red. This is chemical shrinkage. This is the rate of chemical shrinkage. So this would be something very similar to the heat. The dq dt curve. This is the rate of reaction that's taking place. You can see initial set shown here in red, and we'll talk a little bit about initial set in another minute. Final set when people are starting to walk on the surface of the concrete. And then you'll notice the yield stress of our paste plotted as a function of the age of the specimen, and you'll see that it was very, very low, very, very low, very, very low, and then all of a sudden the yield stress starts to rise. And it starts to rise before we get to the time of initial set, and we think that this is something that's actually important. And if we take a second to look at some of the pictures, you'll remember that we had our initial system where we've got the cement particles swimming in water. So our cement particles are shown here in white. We've got the water or the fluid that they're swimming in. And if we were to be shearing this system, we're to be pushing the top portion of the graft over to the left, pushing the bottom portion over to the right, we would notice that we would have some yield stress when we tried to do this, just to get the system moving. And then we would have a little bit of viscosity, but there really wouldn't be a whole lot of resistance, because we've just got cement particles swimming in water. So we're basically just moving these particles over top of one another. Well, as the system begins to hydrate, those particles start to grow. They start to get bigger. We have chemical shrinkage that reduces the overall volume. We start to get things starting to develop inside of the pore solution, and we notice that that yield stress is going to start to rise. And it's going to continue to rise, and where we're going to start to see this huge jump start to take place is all of a sudden once these particles start interacting with water and start banging into one another. And that's where we're going to start to see the shear stress go way up. So really, when we're talking about looking at some of these things at early ages, we're talking about something that's really changing from this fluid state, like our McDonald's milkshake, which is probably one of the worst milkshakes that's out there because it's way too fluid, to something that's in this Sockwood state, which is what we're looking at for our concretes, where we've got something that's much more like a Wendy's Frosty. You could try to pump it using the straw technology they provide at Wendy's, but you got to just break down at some point and start shoveling it with the spoon. All right, because it's just got too high of a yield stress, too high of a viscosity to be moving that material until we end up with a solid. Now there are a couple other tests that we could do. One of them is simply the penetrometer test, where we're going to pull the lever down and we're going to measure the surface strength of the system. One of the things I'd like to point out here is you'll see that it starts to rise and then it starts to really take off. Another test would be the Vicat test, where you're going to take a pin, you're going to have a weight on top of that pin, and you're going to push the entire system down into a paste. And you can actually start to relate some of these numbers together. So if we take some of the rheological data, the rheological data is this blue data that we've seen here. You can take this and compare it with the yield stress that we could compute from the Vicat needle. And what you would see is that these are very, very similar types of data. They start to match up if we look at these in terms of both yield stress. The big thing is most of the rheological data we're going to stop before the system really gets close to setting, because we're really trying to measure what's happening in a fluid and we just don't have the capacity in that system. Once we start to get into the Vicat needle test, now we've started looking at something that's much, much closer to set and has a higher yield stress, has a higher viscosity, because it's getting very close to a solid. Okay, other things that we want to look at when we start to worry about our water reducer: slump loss. If we look at slump, our typical material that shows up on site, one of the things that you will learn is that slump is not a material property. If you don't like the slump you got the first time that it came out on site, try the test again, because it will vary because of the testing. It will also vary because the slump is varying at early ages because of the time that the concrete is hydrating, the cement is hydrating in the system. So just like we showed on the previous graph, we have the yield stress in the material changing as a function of time because the system is hydrating. We would expect the slump to be decreasing as a function of time because the system is hydrating, we're losing water. This value is typically referred to as slump loss. One of the things that people commonly report is that certain plasticizers have quite a bit more slump loss, more variation in the slump at early ages. Now the one thing that I will point out here is one of the reasons we note that it has more slump loss is because there's actually more slump to lose. The water reducer makes the system a whole lot more workable. So we've got a lot more of the system that's being workable, but by the time it sets, it's going to have the exact same slump. At setting time, the slump of our concrete is going to be 0. So it's got to get somehow from a 7-inch slump, a 5-inch slump, down to that value of 0. And one of the things that people get really worried about with using water reducers is the fact that these can change dramatically while the concrete is on site or while the concrete is being placed. So it's an excellent dispersing agent. There are a few things that I will point out. There are 2 or 3 contradicting things, and this is why sometimes you will see some of the water reducers listed as accelerating types, or some of them listed as retarding types. They would accelerate hydration simply on the basis of the fact that you've created a lot more surface area that's exposed to water. If we look at a comparison between the top picture and the bottom picture, in the top picture you've got flocks that are created, so all the cement particles are kind of bundled up against each other. All right? And those particles don't have as much of their surface area exposed to water. On the bottom, each one of these is acting like an island, so the whole thing is exposed to water. They may also be considered as retarding admixtures, though, because they're going to have chemistry on their surface, whether they're polymer chains on their surface, whether they're altering the charge on the surface. So you'll actually see quite a bit of difference depending upon the chemistry of that particular water reducer on whether it accelerates or retards the overall performance. High slump loss can be experienced. A lot of times what you will see is the water reducer actually being dosed or added in the field. When I was working in Pennsylvania, it was not uncommon for us to send a jug of brown juice out to the site when the truck would leave, and they would actually add the water reducer on site right before it was leaving so that they would not be losing that slump at early ages. Typically, you are going to need a dispersant for really tight systems. If you're using something like silica fume, you're trying to get a high-performance concrete, you need to have a dispersing agent in the system. Water reducer almost becomes essential. Questions on water reducers?
Does the time of addition of superplasticizer affects the amount of dispersion or not?
The amount of dispersion... Does the time of the addition of the water reducer affect the amount of dispersion? I'm not 100% sure on the amount of dispersion. I know it will change where the materials end up, depending upon if they're reacting mainly with the C3A, or if they're reacting with the entire system, or if they're forming into the hydrated products. So you'll get different efficiencies when they're added. The other big thing that you'll notice is if they're added before the entire system has the opportunity to be wetted, you will get less efficiency from your plasticizer. And a typical example of this, to try to make this a little bit more tangible, one of the things that you will notice is some people in the field would like to add the plasticizer for various reasons onto the fine aggregate when it goes into the back of the truck. It's a little bit easier. They claim that it's easier for them to add it, and that way it's a little bit more consistent. One of the issues is if you've got a real dry fine aggregate, the dry fine aggregate is going to act like a sponge, and it's sucking up the admixture that you're spending money on to put into the system. So you'll see some of that absorbed. You'll also see some of the materials that get caught up in the hydrated products, and once that happens, then they won't be as effective. So that's sort of going back to the question that you had earlier on where they end up. Okay. Jumping ahead to air entrainers. Some of the basics. We've talked a little bit about the basics and the need for air entraining in concrete. What I want to do here is I want to talk a little bit more about some of the other effects other factors that are going to influence air entrainers, in addition to just their overall volume, and then some of the other aspects of some of these mixtures that are important when we start to talk about freeze-thaw. Resistance is obviously going to be related to mixture proportioning. Water to cement ratio is going to be a vital thing that we're going to look at. We need to look at the volume of the air, and then we also will need to look a little bit at the dryness of the concrete. If concrete stays dry, it really doesn't matter what the water to cement ratio is. It doesn't really matter what the air entrainer is. If there's not water in there to freeze, you're not going to have a freeze-thaw problem. As we know, porous materials are going to be susceptible to repeated freezing and thawing. Freezing doesn't occur at 0 degrees Celsius. It occurs lower than this. It occurs because of two reasons. One, the water is inside of a pore that is constricted, so it's in a small space. It also it's not water anymore. You'll remember as soon as that water comes in contact with the cement, things start to come off of the surface. We start to see the dissolution of particles coming off of the surface. But now we have a saltwater solution, a pore solution, and we will see the freezing point of that starting to be depressed. The freezing depends upon the pore size, so a 10 nanometer pore freezes about -10, 3.5 nanometer pore is down to about -20. You can go all the way down to about -50. And even then, some of the water is not going to freeze on the surface of CSH. One of the most exciting things about water is water always looks like Mickey Mouse. So if we see over here, you could put in some eyes. All right, we got Mickey Mouse looking back at us. This is the oxygen with the two hydrogens sticking onto it. But this means that water is going to preferentially line the sides of our pore walls. So you'll remember we were talking a few lectures ago about water preferentially aligning on the surface of the pore walls. It's basically going to line up in this direction, and then we're going to get into a point where we have water that's less oriented in the middle of the pores and is going to be acting more like free water. Now, one of the things, and I believe this was in our mixture proportioning lecture, I had this fantastic slide that said the following up here, and this is out of ACI. It should be emphasized that an admixture is not a panacea for poor mix design or sloppy concrete, blah, 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 blah. This is really true except for air entrainment. Air entrainment can cure a lot of problems. So you'll see air entrainment coming up quite a bit. You can read this. This comes out of ACI 116. Air bubbles, remember, are going to work mainly on the paste portion of the system. And as we talked about last time, these air entrainment are going to be air-filled spaces. They're typically going to be spherical. They're going to be created by the mixing process but stabilized in the system. And then we're going to have these little pressure relief valves, or these air entrainment spaces. About 18% of the paste should be covered by air entrainment. So as you start to use more coarse aggregate, as you start to get higher volume fractions of the aggregate, you'll typically see there'll be less air that's needed in the overall system. Here again is a listing of the different types of materials. These are surfactants, which means that they are surface active substances. So surface active, surfactants. Nobody else was impressed by that? There's a lot of good underlining that went into that. All right, surfactant materials. We said that one end would be afraid of water, one end would love water, and this is basically what's going to form these air and train stabilized bubbles. Here's a listing of some of the different materials that are used to make these up. Now, as mentioned, some of these will be used by other industries. They are frequently pre-diluted before batching. They can be sensitive to things like carbon and fly ash, which we've talked about before. Talk a little bit about some of the characteristics. They will form relatively small bubbles in diameter, somewhere between 10 and 1,000 microns in diameter. They will have quite a bit of their own surface area. They'll make up about 4.5 to 7% of the total concrete. Again, we want them to be on the order of about 18% of the paste. This means that we will have billions of bubbles per cubic yard. All right? You do not want to sit there and get into a contest where you're going to count all the bubbles of air in a cubic yard of concrete. In addition to just the volume, the nature of the air and the quality of the air is going to be incredibly important. We'll say what quality of the air means. It's going to be influenced by the type and the duration of mixing. One of the biggest problems that we will see is the time that the admixture is added and the way that it's mixed in will make a big difference in how it performs. You'll also see there's a little bit of a temperature sensitivity on how the concrete is actually going to perform. So to give you a little bit of an example that you could probably be real familiar with here on how mixing would influence this, most of you have done dishes at some point in your career. Yes, someone did dishes. If not, I'm sure that your sink at home has a nice pile of dishes that you could probably go home and test this out on. If you fill the sink up with nice cold water and then squirt something like Dawn into the system, that nice blue Dawn that you've squirted into the water is going to do what? Sink to the bottom and you'll have this blue-looking snake-like thing across the bottom of the sink. If, however, you squirt the Dawn in while you're filling it up with the water, there's a mixing action. It is going to cause a frothy delight. Okay, so we're going to get some of that air bubbles created, stabilized, and it's going to help you because it is going to remove the grease by helping to stabilize the grease in the system and take it away from what you're doing. Slump is going to influence our air a little bit, and the degree of consolidation or the degree of vibration is going to impact us quite a bit because vibration is there to get rid of the air. Right? So what you want to do is you're going to see the air will change a little bit. Now, I said the nature and the quality of the air is important. One of the most important things is the spacing of these air bubbles. So we talk about volume because it's the easiest to measure, but what we really would desire is we would really love to have a bunch of small bubbles that are really, really closely spaced so that they protect all the paste evenly. You can imagine this if we went to the real extreme. You've got a cubic yard of concrete and you've got 7% air pocket in the center of that concrete. Well, the edges of the concrete don't feel that at all. Right? What you want is something that's evenly distributed. And what they commonly look at is a term called the spacing factor. And the spacing factor really dictates, obviously, how far apart the air bubbles are spaced. This is another example of civil engineers having a tremendous vocabulary and being able to really define something that tells us exactly what we're looking at. When the bubbles are really close to one another, we will see a very high durability factor. And this durability factor is essentially the elastic modulus at any time over the original elastic modulus, how much the system degrades. If these bubbles start to get too far apart, even if the amount of air is right, if the bubbles are too far apart, we're going to see the system start to degrade. Questions on that? Now, there was also another question, I believe, last time that asked if there's such a thing as too much air inside of the system. One of the things that you will notice here is if we add air, now this is air content by volume on the bottom, if we add air, the strength of the concrete will simply drop off because we are increasing porosity. So I believe in homework number 3 you had a simple question on comparing the strength of these different mixtures, and you knew that it was something like porosity over the total volume of the system or porosity over the total volume of porosity that was leading to a reduction in strength. Same type of thing here. If you have air entrainer in the system, you're going to reduce the overall strength. Typically we see sort of the best benefits somewhere between 4 and about 12%. One of the problems you'll get to is you'll see the durability factor, and this is that freeze-thaw number, the ratio of stiffnesses going down over time. One of the reasons this starts to drop off is because the strength becomes too low. So the only real reason that we're worried about getting too much air in the system is because we start to decrease the strength to a point where all of a sudden the system is going to start to become really porous and going to become weak. The one thing I would tell you is if you are going to miss on one side, it's much better to miss high than to miss low. Okay, if you miss low, you're going to have a system that doesn't have enough air and it's going to cause problems. If you miss high, you may see a slight reduction in air content. So normally, let's say we're targeting 6%. If you target 6%, if you're off by 1% in this direction or 1% in this direction, all right, there's not really a big loss in getting a little bit extra air in the system. There could be a big downside in not getting enough air in the system. All right, other things that you want to think about, if you have lower water to cement ratio, you have less water in the system to freeze. If you have less water in the system to freeze, it's going to be more resistant to freezing and thawing. So here's a measure of the freezable moisture in the paste as a function of water to cement ratio. Lower water to cement ratio, less moisture in the system to freeze. When you get below 0.4 water to cement ratio, the system is going to self-desiccate and you're going to have a lot more air inside of the system, a lot tighter system, so it's going to be harder for water to get back into the overall concrete. I'm not going to spend lots and lots of time talking about some of these other issues. We talked a little bit about the reduction in strength. As I mentioned when we were talking about ASR, here you'll see people saying that ASR can be reduced by adding a little bit of air to the system. All you're doing is creating a little bit extra space for that gel to be forming. Some of the things that are going to cause you to use more air and trainer, a finer cement, more surface area inside of the system is going to react faster. Lower alkalis will cause an increase in dosage. More carbon in the cement. Pigments, any sort of coloring agent, higher temperature, and the hardness of the water can all influence how effective that air and trainer is going to be. One of the things I'll mention real quickly here before we end up today is I want to talk a little bit about some of the freezing and thawing action. There are two main features that are going to cause this pressure that generates inside of the concrete. The first one we know is the hydraulic pressure. That's simply the fact that the water is going to expand on freezing. The second, so this is the hydraulic pressure that we're talking about, the 9% increase in volume. The second thing that we'll talk about is a change in concentration that's going to happen in the system. Salt water doesn't freeze, so what you're essentially having is a system that's becoming more and more concentrated. And there's going to be a movement inside of the system that's going to cause an osmotic pressure that's going to also create a little bit of pressure inside of the system. One way that we typically will measure freezing and thawing resistance is we will take concrete and we will dunk it into a tank and put it in a great big freezer and freeze it and thaw it a bunch of times. This tank is actually sitting on the ground. I don't know why it looks like it's laying open, or this is actually in the labs. I think I've got it at some sort of a very odd angle here, but there's basically going to be prisms that are placed in here. These prisms are 3 inches by 4 inches by about 14 inches long. There are two procedures in ASTM 666. One is procedure A, they freeze and they thaw in water. One is procedure B, where they freeze in air and they thaw in water. Both of these are generally thought to be relatively bad tests. One of the reasons that these are relatively bad tests is because freezing and thawing is not based simply on freezing and thawing. It's based on the rate at which water can be absorbed into the concrete, the degree of saturation, how fast the test is performed. So there are several other things that go into determining how successful a concrete is going to be. You can see some typical numbers here. I believe this is from some of Ken Hover's work out of the PCA guide. You can see here is a high water to cement ratio concrete where it degrades. This is, again, that relative dynamic modulus degradation and stiffness as a function of the number of cycles. You will see that these other mixtures take a longer period to degrade. One of the reasons they take a longer period to degrade is it takes longer for water to get into a more dense system. So this is generally a test method that's okay, but it's not the best test method I think that's out there. Good quality aggregate, enough cement inside of the system, and a minimum compressive strength. You want to avoid places where your concrete can saturate. Here you'll typically see places on concrete slabs where they'll degrade. Some of the other things that I'll talk about next time are issues related to mixing, transporting, and consolidating our concrete. One of the most important or one of the most interesting graphs I've ever seen is this graph right here, and it's probably arises out of my fascination with actually finding an answer to where this number comes from. When we talk about batching concrete, we'll find out that you can't have more than 300 revolutions on the truck when they start to discharge it on the construction site. One of the reasons why we want to limit the number of revolutions is presented in this graph. At about 300 revolutions, we start breaking the air in the concrete down. So we'll end up class very quickly next time talking about batching, and then we will move on and we'll start to talk about some other topics. Accelerators.